Hello everyone, hope you are all doing fine. Welcome back to the third lecture on equivalent resistance series lecture. So in this video we are going to learn about how to find the equivalent resistance by using current division method. Okay, this is one such method where which we use in order to find the equivalent resistance. Of course, the Kirchhoff laws are involved in this kind of method, but anyhow we will be able to understand it clearly by the end of this video. So my name is Vijay Krishna and you're watching UpPhys channel. Let's get started. Let's look at the three steps that I have mentioned here. Read out these three steps that we are going to follow in order to find the equivalent resistance by using this current division method. We will go through one or two examples as well to make you understand it even better. Okay. So first, I'm reading out the steps that I'm going to follow. Assume a total current entering through the input terminal of the circuit. Let us say you are given with a circuit. Okay. So from a voltage source, energy source, current is coming and reaching to a terminal where it enters into many number of branches of the circuit. Okay. So we are going to assume that current and then split the current in the sections of the circuit using the current division rule. So we divide the current across all the branches from which are starting at that terminal, and write the KVL equation by considering the loops. So these are the three steps that we are going to follow in order to find the equivalent resistance by using this method, current division method. Okay, don't worry about the statements. You don't need to by heart it. Just follow the procedure, practice it for for about 3 to 4 problems. You will be able to crack it. Okay, right. Let's look at the example. Okay, here I have taken a bunch of circuits which have been arranged such that it forms a simple cubic structure. Okay, now this is a simple cubic structure and I have considered as the terminals over here. Now the energy source is connected exactly at the opposite corners of the cube. So this is the voltage source that I have applied to the circuit. Let us suppose V. Whatever the voltage that we take, it doesn't matter because we concerned about the equivalent resistance of this entire circuit. Okay, so I have taken it as V. Okay, right. You can even take a number, 100 volts, 120 volts, maybe 220 volts. You can even take any number. Okay, so as this is not our concern, I have taken V as a variable only. So V. From this V, let us say the total current flowing in the circuit is I. Let us suppose I. If I current is flowing, due to symmetry, this current I will be divided into 3 branches. Here, here, and here. As I can see, here, here, and here. Some current flows through this branch, some current flows through this branch, and some current flows through this branch. From symmetry, the current will be same. Okay, as the terminals of the battery, terminals of the voltage source is connected across the opposite corners. Due to symmetry, current will be divided in equal parts. As current is divided in equal parts, I am taking the total current as 3I. I'm taking the total current as 3I. Let us say this is 3I. Total current as 3I. And this branch current will be I. This branch current will be again I. This branch current is also I. Hope my point is clear, right? So I'm looking at this current. This current is flowing in this direction, and at this location, again current gets divided. Some current flows into this section, some current flows into this section. Let us say in this section the current flowing is I by 2, and in this section is also the current flowing is I by 2, because again due to symmetry. After dividing, it is flowing through 2 resistors in each branch only. So this is one resistor, this is one such resistor, this is one resistor, this is also one resistor. Both the current is flowing through 2 resistors during along its path. So it is divided into I by 2 and I by 2. Now coming to this current, okay, this current also divides into two parts, which is I by 2 again, and here also I by 2 again. This is also flowing through two resistors along its path, and this also flowing through two resistors along its path. So current is divided in equal parts. Now look at this current. This current is flowing right here, and right here it is divided into two parts. One is I by 2, the other one is I by 2 again. Okay, now again at this branch, this current is coming towards the junction, this current is also coming towards the junction. They both add together, and here it gives total current I. Total current I. Now let's look at this one. This current is flowing in this direction, this current is also flowing in this direction. Both these currents will add up and gives the current I through this branch. Through this branch. So current I, and here also current I. Now this current is flowing in this direction, this current is flowing in this direction. These two will add up, these two will add up, okay, and gives the current I again. Now this current is coming towards this junction, this current is also coming towards this junction, this current is also coming towards this junction. At this junction, all these currents are coming towards the junction. All these together gives a total current of 3I. Whatever the current which is leaving the battery, I mean, as I've already told you, total current leaving the battery is just equal to the current which is entering the battery. Okay, so the circuit is completed. The current division is also completed. Okay, now we will take any one loop to solve it. Okay, let us take okay, now I'm taking it as A, B. Okay, sorry, we have already A here. We have A here, so this is B, C, G, and again P, here I'm taking it as P, Q. Okay, now I have a loop P, A, B, C, G, again Q. Okay, now from loop P, A, B, C, P, A, B, C, G, Q, G, and again Q, again P. This is our loop. Now we are going to apply KVL, Kirchhoff's voltage law, or Kirchhoff's voltage law. Okay, Kirchhoff's voltage law. Okay, now I'm taking the direction as okay, something like this. Okay, direction of the loop, I have taken it in clockwise direction. Okay, now I am starting from the battery, the power source, the voltage source. As the potential is rising from lower potential to higher potential in the direction of loop, I am taking it as positive V, and potential drop is there because current is flowing from higher potential to lower potential. This is higher potential, lower potential. Loop I have considered from higher potential to lower potential. Potential drop is there, so negative sign that I am taking. I into R. I into R is the potential drop across this resistor. Now coming to this resistor, the current is I by 2, resistance is R in the direction of loop, and again there is potential drop I by 2 times R. I by 2 times R. We have another resistor which is I and R again, which is I R is equal to 0. Is equal to 0. Okay. Now V minus IR 2 IR minus IR by 2, which is how much is it? 5 IR 2 IR 2 to the 4 plus 1 5 IR by 2 is equal to 0. That means V is equal to 5 IR by 2. V is equal to 5 IR by 2. Instead of having these many resistors, as I am finding the equivalent resistance means the resistance, the resistance of the resistor which is replaced in the place of this entire bunch of resistors, right? If I simplify this circuit will appears like this. This will be our battery voltage source, and this will be our equivalent resistance, and the current flowing through the circuit is that I have taken it as 3I. Okay, if I use loop law again, or else simply you can say it as Ohm's law. If you use loop law, the potential is rising positive, and here the potential drop is there minus current times resistance or equivalent is equal to 0. That means V is equal to 3I R equivalent. 3I R equivalent. This is equation number 1, and this is equation number 2. If I compare these two, or else these two equations are equal. So if I compare these two, 5IR by 2, 5IR by 2 is equal to 3IR equivalent. 3IR equivalent. Okay. If I cancel out the common terms, what am I getting for the equivalent resistance? So 5 by 6 times R. This is our equivalent resistance. This is our equivalent resistance. Even this same kind of method you can also apply to when the power source, voltage source is connected across any other terminal, something like okay, this is the cube that I have taken, this one, okay, cube of resistors, and I have connected the voltage source across the corners of the face. If this is the face, opposite corners of the face are these two. I have connected the voltage source across the corners of the face. Okay, in that case also the current divides. Here I1, let's say total current flowing is I. Here it goes I1, here it also goes I1, here goes I minus 2I1. Okay, so current flowing towards the junction must be equal to current flowing away from the junction, right? And why I have taken these two currents equal? Because after dividing, this current is only flowing through these two resistors, right? And after dividing, this current also flowing through these two resistors only. Their path is similar, right? So because of similarity, the current is divided into same. Okay, and the rest of the current is flowing through the rest of the branches. Hope my point is clear. Now you can use Kirchhoff's law. You can take two or three equations to solve to find I1 and I2, not I1 and I2, to find I1, and then you can express the I, and then finally you can equate the potentials. You can take any potential here, any voltage difference here, any voltage difference V. Okay, you can compare the equations in order to find the equivalent resistance. Hope my point is clear. Okay, if you want me to give one more example, I would like to give one more example to you to make you understand it even better. Okay, let's take one more example. Okay, right. So this is one such resistor, and this is another such resistor. Okay, now these two are given to a battery of potential difference. I don't care about the potential difference value, whatever I take, I'll get the same answer. And these two branches have been connected with another resistor. I'm taking this as 5 ohms and this as 10 ohms. This is also 10 ohms and this is 5 ohms. Okay, and here we have 5 ohms again, right? This is actually called unbalanced Wheatstone bridge. Okay, which we will discuss in the later lectures. But anyhow, we use current division method to solve this question. We are going to find the equivalent resistance, and of course you can find the current in each branch as well, each resistor as well. Okay, I'm taking the total current out of the battery is I. Now, as the current coming here is I, the current going into this branch, this current is being divided into two parts, right? And here it is I1, and rest of the current is flowing into this section. As total current flowing towards the junction is I, this is I1, rest of the current will be I minus I1, right? Okay, now current flowing towards this junction is I1, and this is I minus I1, right? Now from symmetry, here we have 10 ohms, here we have 10 ohms. So the current that flows through this 10 ohms, that means total current that we have to acquire is I only, no? So the total current coming out of these two branches, right? These two branches. As the current flowing this 10 ohms is I minus I1. Here also I am taking it as I minus I1 due to symmetry, and here it is I1 which is flowing through 5 ohms. Here also I am taking it as I1 which is flowing through 5 ohms again. I1, I minus I1 both together is giving the total current of I1. Again, due to symmetry, we have divided the currents. Okay. Now, now let us find what is the current that is flowing through this branch. Flowing through this branch. Okay. Now, let us apply junction law at this location. If I apply the junction law at this location, the current flowing towards the junction is I1. Current flowing towards the junction is I1. I'm taking this current as X, let it be. I'm going to find X. So it is flowing away. So X, and this current also flowing away, plus I minus I1. I minus I1, sorry. X plus I minus I1. Hope my point is clear. According to junction law, Kirchhoff's junction law, currents flowing towards the junction is equal to current flowing away from the junction. Okay. So flowing towards the junction is only one current, which is I1, and flowing away from the junction we have two currents. One is X, the other one is I minus I1. We need to find X here. So I am rearranging the equation for X. X, this I comes this side and minus I1 comes this side. I'll be getting 2I1 minus I. 2I1 minus I. I'm going to take this off, and here the current is 2I1 minus I. 2I1 minus I. I have everything ready. Now I need to use the Kirchhoff voltage law. Okay, right. So to do so, I'm taking a loop. That loop is this one. And the direction is clockwise. Direction is clockwise. Okay. Loop is in the direction of the current. So potential drop is there. Potential drop minus 5 I1. Minus 5 I1, and here also in the direction of the loop, so potential drop will be there, minus, here it is 5, 2I1 minus I, 2I1 minus I, and here the current is opposite to the direction of loop, potential is rising, so potential difference, what is it, I minus I1 times 10, 10 into I minus I1 is equal to 0, is equal to 0. Hope my point is clear. As the loop is considered in this direction, current is also in this direction, high potential to low potential, potential is dropping. So I've taken potential across this resistor is negative. This is also the same process. Potential drop across this resistor is also negative. Whereas current is flowing in this direction, loop is considered in the opposite direction, right? From lower potential to higher potential, the loop direction is, hence the potential is rising. So 10 I minus I1 is the current in that branch. So simplify it, 5 ones, 5 ones, 5 twos. This is minus I1 minus 2I1 plus I, here it is plus 2I minus 2I1 is equal to 0. We have I1s and I's. If I add it up, minus 2I1 minus I1 is minus 3I1 minus 5I1. 3I is equal to 5I1. 3I is equal to 5I1, and here I1 is equal to 3 by 5I. I1 is equal to 3 by 5I. So, okay, now listen to me very carefully. I'm taking another loop, as we have two variables. I want to find I don't know I1 as well. So in order to find I'm taking another loop, which is this one. Okay. Okay. Again, clockwise. I'm starting from the potential difference across the battery itself. As the potential is rising in the direction of loop, potential is V, that is V, and loop is considered in the direction of currents, potential drop is there. So minus 10I minus I1, and here also current is in the direction of loop, so minus 5I1, 5I1 is equal to 0. We have only three components, so three terms. Okay, and I know the I1 value, so V minus 10 I minus I1 is 3 by 5 I1, sorry, 3 by 5, okay, 3 by 5 I minus 5, 3 by 5 I is equal to 0, is equal to 0. Here we have 5, here we have 5, cancel out. If you simplify this one, this entire thing will come out to be 2 by 5I, 2 by 5I, and if I rewrite this equation, I'll be getting V minus minus 10 into 2 by 5 is something 2 times 2 to the 4I, 2 to the 4I, 4I. Now here we have 3I is equal to 0, right? Now V is equal to 7I, V is equal to 7I. Okay, let's simplify it even further. Instead of having this entire circuit, let us say I have only one circuit which is equivalent to this entire circuit. Okay, so equivalent circuit that I am drawing, that will be this one, a potential drop that I have applied, which I, okay, B, and here this entire circuit is replaced with one resistor R equivalent, R equivalent. Now current flowing through the circuit is I, as I have already mentioned, I. Now if I apply the loop law like this, okay, then what am I getting? V minus I into I, R equivalent, I into R equivalent. That means V is equal, R equivalent is equal to 0. V is equal to I into R equivalent, right? Let us say this is equation number 1 and this is equation number 2. Hope my point is clear. If you compare V is equal to 7I, V is equal to I, R equivalent. If you compare these two results, V is equal to 7I, V is equal to I, R equivalent, I will get cancelled, R equivalent is equal to 7 ohms. This will be our answer. I hope the entire explanation, entire steps that we have followed are completely understandable. Okay, so what are the steps that we have followed? We have assumed the total current, first step, and this current is obviously dividing into many branches at the input terminal, now we have to divide the currents according to symmetry, according to our understanding of current path. Okay, understanding of path. So I have divided the currents. Okay, if required I also use the junction law, otherwise it is not necessary. Okay, whenever required we use the junction law as well. As we required to use the junction law, we have used the junction law in order to find the current in this branch. Okay, and we also use the junction law in order to find the current in this branch, because total current coming into the junction is I1 is flowing away, that means remaining current should be flowing into this branch. That is also junction law. So we have used junction law and voltage law. We have taken multiple loops and we have calculated the we have simplified the equations and we have compared the results to find the equivalent resistance. This is what we have done in the earlier case as well. I hope this entire lecture is understandable. I hope you have clearly understood the method of finding equivalent resistance by using current division rule. So yes, if you have any doubts, please comment below. If you are facing difficulty in understanding, watch it 1 or 2 times more, so that you will be able to understand it very clearly. Okay, I hope the lecture is helpful to you. If you find the lecture is helpful, please do like, share, subscribe, and don't forget to hit the bell icon in order to get the notifications as soon as I upload the videos. So that's it in this video. Thank you for watching. See you in the next video.